Well, welcome to day 2 of Granville Fest, and it's my pleasure to be the chair this morning. Our first speaker is Ken Ono from the University of Virginia. He will speak on Sato-Tate type distributions for families of hypergeometric varieties.
All right. Good morning, everybody. Thank you for coming. I know it's I'm just going to get started. I think we're starting a couple of minutes late. Happy birthday, Andrew. I'd like to remind everyone that I made my birthday comments yesterday. And for those of you who weren't there, let me just say I certainly wouldn't be here in any sense had it not been for Andrew, quite frankly, rescuing me in the early 1990s. So today's lecture is called Sato-Tate type distributions for families of hypergeometric varieties. All of the results will be completely explicit. And so what better way to start in terms of explicit things than with an example? So an example that you could compute would be, say, for this elliptic curve given here, y squared minus y equals x cubed minus x squared. And for primes p, there's an integer a of p, which we refer to as the trace of Frobenius, which due to Hasse quite nicely lives in this interval from -2 root p to 2 root p. And for every prime p, what is the significance of the number a of p? It's an error term. It's the difference between the number of points on your curve over the finite field fp and p plus 1. In view of the width of this interval, it's traditional to normalize the number of numbers a of p, and we do that here in this picture. So if you divide a of p by 2 root p, that gives you a number in the interval from -1 to 1. And if you do a lot of computation and begin to collect them, you can find photographs like this that you can steal from Drew Sutherland's website. And you'll find that for the prime 10 to the 9th, these numbers a of p over 2 root p begin to give you a glimpse of the squashed upper half semicircle. Of course, this is an illustration, a glimpse of the very famous theorem of Taylor and his collaborators. And just quite frankly, this is a huge theorem. It helped contribute, was one of the main reasons that Richard won one of these breakthrough prizes 7 or 8 years ago. And it's the statement that for every elliptic curve without complex multiplication, if you associate an angle with each prime p, which is just a reformulation of what we called a of p, then for any subinterval from 0 to pi, say alpha beta, if you were to just count the number of primes up to x, for which this angle is in this interval alpha beta, compute the proportion of those primes, this converges to the definite integral of sine squared theta d theta when restricted to the interval alpha beta. So the picture is probably more than enough to indicate or formulate this conjecture as a major theorem, as I think all of you know. This theorem has inspired a lot of work. Perhaps you're familiar with the work of Kedlaya, Sutherland, and others. And the direction that I want to go into is slightly different. And so what I'd like to ask are the following questions. What about distributions for families of varieties over fq, but now where q goes to infinity? So imagine you have a family of varieties and you want to sample them at random. And as the finite fields get larger, are there natural distributions? A question that you might not be thinking about if you haven't been in the field would be, how generic are these semicircular distributions? Because at the end of the day, if you talk to people who are not familiar with automorphic forms, they don't understand what the hoopla is about just getting the upper half semicircle. There's lots of ways of getting the upper half semicircle, and you don't need elliptic curves to do that. And so, as we all know, that's really not the point. The point is about deriving new tools for studying arithmetic geometric questions. How exotic can they be? If you're familiar with some of these works, you know there are 50 or so various kinds of compact Lie groups whose random matrices are expected to model these distributions. And finally, is there a structural framework for explaining further distributions? For those of you who are familiar with the recipe of Sayre, that is one answer. The question I want to talk about are families of varieties. And the families of varieties that I want to talk about arise from hypergeometric functions. If you're familiar with the recent work of Roberts and Villegas, they wrote a beautiful article in the notices of the AMS. So the kinds of varieties I'm talking about are the ones that you would find in their program. So to be completely explicit, this is in joint work with my student Hassan Saad and former postdoc Neelam Saikia. The theorems that we prove can be visualized by means of these two pictures. So I want to show you three families of hypergeometric varieties after explaining what that means. And it'll turn out that the distributions exactly along the lines of what I just described will be illustrated by pictures like this. On the left, you see the squashed upper half semicircle. And the right, you might see something that's a little bit different from what you may have encountered before. And I'd like to begin to explain how the geometry dictates the variation for these distributions when you study families of varieties. If you're wondering about the letters AOP, I want to indicate there are many kinds of K3 surfaces with different invariants, varying Picard ranks. So when I talk about AOP, I'm referring to a family with generic Picard rank 19 that I wrote about with my former postdoc, Scott Algren and David Peniston, so many years ago, and I just call that AOP. Just a very brief refresher on the kinds of varieties that arise and often arise in the context of mathematical physics. We're interested in varieties that are associated to solutions of differential equations, which are referred to as the Picard-Fuchs equations. And these are ordinary differential equations whose roots are periods of varieties. And it's not very difficult to use the standard theory of classical hypergeometric functions to give closed formulas for these periods. And I assure you that you've seen this before. These hypergeometric functions are these infinite power series in X, whose coefficients are ratios of products of factorial type numbers. And I assured you that you've seen this before, and I think you have, because the first example of this arises quite naturally in the theory of elliptic curves, the Legendre normal form elliptic curves. So Gauss provided for us the very first example of a Picard-Fuchs hypergeometric variety. So if lambda is a real number, and you let omega be its real period, for the Legendre curve indicated by y squared equals x times x minus 1 times x minus lambda, that's a one-parameter family. It's a moduli space of elliptic curves over the real interval. And Gauss famously proved that the classical 2f1 hypergeometric function with the parameters 1/2, and 1, evaluated at lambda, returns the real period of the elliptic curves. A very famous example. And if you haven't studied these works by Roberts and Villegas and or others, or maybe even some of the early work of Dwork and Deligne, you can go back to those papers and you'll discover this was like a first primary example for developing some of these theories. Might come as a surprise is that many people are still looking for more families of varieties, and that should be the context in which I invite you to read some of those works. And as an example, here's a fairly recent paper from 2010 by Dermot McCarthy, where he just finds new formulas for periods of elliptic curves. I think I called these curves Clausen curves. These are elliptic curves given by the equation y squared equals x minus 1 times x squared plus lambda. And it turns out that the real period of those curves is given by this 3f2 hypergeometric function, where the argument is replaced by is lambda over lambda plus 1. What you will notice is that the periods, which are the numbers in red, in this case, is a perfect square. The 3f2 gives the perfect square of the real period. And what's really important about that is that that's a glimpse of things that come up naturally in algebraic geometry. If you start studying Kummer surfaces, some of the first examples that you'll describe arise as products of elliptic curves. And already the hints of a lot of that are present in the theory of special functions. And in this case, it is exactly that. There might not look like there's a K3 surface sitting here in McCarthy's theorem, but there is indeed. So let me explain. So the three families of hypergeometric varieties that I want to talk about today, this is just the beginning of lots of results of this type. The first two are elliptic curves, the Legendre family and the Clausen family. So-called Clausen because there's a famous formula in the theory of hypergeometric functions that relate 3f2s to 2f1s, and it involves taking a perfect square due to Clausen. K3 surfaces, this is just one particular example of a generic family of K3 surfaces with Picard rank at least 19. There are not very many of them, but they're very special. Oh, I guess 20 years ago, we discovered this family called X lambda. It's given by this. The parameter lambda occurs as a coefficient on Y and the last factor. And what I want you to imagine is, what if I wanted to take a large finite field, sample lambda randomly over that finite field? How would the geometry in terms of counting rational points vary given this geometry? So for those of you, maybe I am the first person to use the word modular form. Modular form, actually, they will appear in this talk. It's like against the law for me to give a talk without saying modular form somewhere. But one of the reasons I'm attracted to this particular family is that some of these special cases for special values of lambdas, just the few ones that are shown here, correspond to modular K3 surfaces. Not quite modular as you would expect from Taylor-Wiles, but close enough. So it's well known that there is no infinite family of K3 surfaces that are generically modular. At most, there are finitely many specializations that are modular, and this would be one of those so-called rich families that have a number of modular examples. The modular form, if you're wondering, has weight 3 for these 3 cases. But I said generically, that will be false. There's a very beautiful mantra that I think should be much better well known than perhaps it is. The ideas you can find seeds of in work of Dwork and others, but I'd like to make it completely explicit here. There's a magical phenomenon that relates classical hypergeometric functions to both p-adic and finite field hypergeometric functions. And it really is magic. There are no direct proofs that say if you prove a theorem about classical hypergeometric functions, it immediately transforms or can be transported to the setting of p-adic or finite field. There's no theorem like that, but there is a mantra. So let me explain that mantra. The mantra is indicated here in this picture. So in the first displayed equation, I say that it could be that real periods for Picard-Fuchs varieties are given as special values of a hypergeometric function. There's nothing special about the parameters 1/2, 1/2, and 1, but I'm just leaving it there because that's the topic of today's talk. For a finite field FQ, if the characteristic is odd, there are definitely going to be characters of order 2. For any divisor of Q minus 1, there will be characters of those orders. And so the idea of replacing rational arguments by characters is done quite specifically in terms of divisors of Q minus 1. So it turns out that there are finite field hypergeometric functions whose subscript is denoted here in red by FQ, whose special values by law, it seems, count points on elliptic curves. It's not the stuff of Galois representations, although you may use the Galois representations to study them. By law, they're much more innocent. So let me give you an indication of this. First of all, how do you compute points on varieties? You usually use things like Gauss sums, Jacobi sums, so on and so forth. And there are many properties of Gauss and Jacobi sums that have analogs in the theory of special functions, usually involving like the gamma function, which interpolates factorials. So going back to the 80s, it was already recognized that a finite field hypergeometric function evaluated at lambda counts points on these elliptic curves. I learned about that as a graduate student, and shortly thereafter, I wanted to study other curves. So I studied the Clausen curve. But by that time, I knew what a K3 surface was. So let me skip this K3 surface and say, for the 3F2, that family of K3 surfaces I showed you, I knew that the 3F2 hypergeometric function evaluated at minus lambda by law knows how to count points. So the question then is, if you want to study varieties, the distribution of rational points on varieties of large finite fields, armed with theorems like this, the variety vanishes. It becomes a counting problem on values of functions, right? In the first case, we just want to study the 2F1 functions and figure out as lambda varies over the Q many points in FQ, how do those values vary? And if you want to study the number of points on this K3 surface, you no longer need the K3 surface. You have a function called 3F2, and you want to understand how its values are varied as you sample randomly from the finite field FQ. So I'm going to show you the definition of the finite field. I'm going to explain that. I'm going to explain that not precisely, but you'll see some different bounds in a moment, and then you'll infer exactly how this changes with the parameter. I didn't define for you what is a finite field hypergeometric function, so I'll just loosely define it for you here in this picture. The letters capital A and the letters capital B are characters. They're just homomorphisms from FQ star to the root group of roots of unity. The characters are, of course, linearly independent. They span the set of functions over FQ, so why not? This power series over the characters chi, the powers of x and an ordinary power series are replaced by the values of chi of x. And so all I have to do is describe to you what these strange binomial terms are. If we're going to count points, they should be coming from some sort of character sum, and they are. Each of these A above B's are just normalized Jacobi sums, the sorts of things that you would come across first in counting points at all. And it turns out that a lot of the things that you know about Jacobi and Gauss sums, factorization formulas, are all just analogs of classical facts that you already know about the gamma function. And it was with this idea in mind that these functions might have the right to be the analogs for the purposes of computing local zeta functions for varieties, the classical functions that give you the periods. And the last couple of theorems I show you that showed examples of that. So if we want to do Sato-Tate type stuff, you prove theorems like this, and it becomes a question of how do you compute these distribution problems for functions that are assembled from linear combinations of products and ratios of Gauss and Jacobi sums. So more precisely, I'm just repeating myself. Now, what is a limiting distribution of this root Q 2F1 as lambda varies over the finite field? These are numbers that will populate the interval -2 to 2. And as I've mentioned, these are the error terms. These are genuinely the traces of Frobenius for the Legendre curves. This isn't new. This is a very easy theorem, but I wanted to use this as a starter. So you could prove for any interval between -2 and 2. So I think I'm addressing to some extent Zev's comment. This is really the interval -1 to 1, but I want to emphasize the role of the hypergeometric function. So I'm normalizing it to be from -2 to 2. And as you'll see, when we go to the next case, there will be an interval from -3 to 3, and then you can infer from there what's going on. So what's the point? If you pick any subinterval from -2 to 2, call it A, B, let the characteristic go to infinity and count how many special values lie in this interval. In this interval, it converges to the ordinary Sato-Tate measure. Any one parameter family, any moduli space of elliptic curves with non-fixed J invariant will satisfy this distribution. In terms of random matrices, this is now very well known. This is just the statement. All the proofs somehow go through observations like this. Whether you're dealing with symmetric power L functions, or in this case, mth power moments of my functions, all the theorems boil down to relating, at least in terms of the random matrix model interpretation, proving that the even power moments, because the odd ones vanish, that the even power moments correspond to the even power integral moments over SU2 for the traces. So if we turn to the K3 surface, right, which is much more interesting, you could ask, what is the limiting distribution of the renormalized 3F2 values, which are now in the interval from -3 to 3? These are the error terms for the point counts on these K3 surfaces over FP. Our theorem is this. This is not so exotic. Right now it says pick any interval from -3 to 3, pick finite fields of the shape whose order is P to the R, and let the characteristic go to infinity. So you might already be wondering so I don't want to get into that. The theorem that's stated here is we're picking all finite fields of order P to the R and we're letting the characteristic move. And for those of you who are wondering the dependence on R, you're right. Those are all questions that none of us have thought about yet. We're much more interested in collecting an atlas of these varieties. So what this says is a limiting distribution as the characteristic goes to infinity for the proportion of normalized values in an interval converges to a definite integral of some function called f. So it says that there's an answer. What is that answer? That answer is this very obnoxious looking function f. It doesn't look like, well, maybe some of you recognize it. For example, if you're familiar with the methods of Sayre and his JAMS paper, you might recognize some piecewise defined functions in connection with Hecke eigenvalues. But let me skip that. This says that there is an answer. For those of you who can graph instantly in your head, you will have already recognized that my theorem gives a picture like this. I really like this picture for a couple reasons. It's not a semicircle. I showed this to my wife while we were starting to write this paper. Well, it looks like Batman. So yeah, that is Batman. So our theorem is that the distribution of error terms for K3 surfaces with Picard rank 19 is Batman. And I'll tell you about what that means in O3. But before I say that, there's several things I really want to point out. The first thing I want to point out is that your eyes do not deceive you. This isn't really Batman, because Batman's hood, his ears end. There are vertical asymptotes at both -1 and 1. I love that. And one of the reasons I love that is it gives us the opportunity to ask new questions, which are quite, I think, pleasing. So what I asked my student Hassan Saad to do is make this effective and explicit, not just because that's what you're supposed to do, but because there's a beautiful corollary as a consequence. So what Hassan did was prove this. Capital A sub lambda of P is just shorthand for what I was previously calling the renormalized 3F2. And he showed that as P goes, not as P goes to infinity, for every prime at least 5, the difference between the proportion of primes whose error terms lie in this interval and the expected definite integral is no more than 111 over P to the 1/4. So what I like about that is I'm sure you can imagine Batman's ears go off to infinity. Imagine drawing a horizontal line at y equals t, and you could ask the question, when is my finite field guaranteed to be large enough that Batman's ears extend to be above y equals t? And that's an immediate corollary, of course, of his theorem. In terms of random matrices, this is the O3. So if you're thinking, is it generically true that distributions of like Kummer surfaces arising from symmetric squares of SU2 is O3? No, that is not true. It's true 100% of the time, but it is not always true. So let me tell you what is true. So here, again, only the even moments matter. There's an extra symmetry, so the odd moments vanish. Turns out that the even power moments of our function correspond to the even power integral moments of the real orthogonal group O3. If you were wondering, you will recognize the theorem I'm describing is about families. And often it's the case that when you study families, families should be easier than studying the individual variety. This is exactly reversed in this case. Believe it or not, proving a theorem about what's called horizontal Sato-Tate, where the variety is fixed and the P is moving, is much easier, despite the fact the graph is much more exotic. Prove that, I run an RAU. I think some of you in the audience have been in it, so thank you for coming. It's great seeing you again. This summer we ran an RAU, and if you're wondering about horizontal Sato-Tate, instead of sampling lots of varieties at once, I'm going to fix an X lambda. Two of my students and a former, well, I guess they're all students. Jesse Thorner was like an old student now. But in our REU, we wrote this paper. They wrote this paper. If you fix a lambda at random where the K3 surface is not degenerate, so lambda isn't 0 or -1, then the horizontal Sato-Tate comes in one of 2 flavors. So X lambda is fixed and you're counting the number of primes P for which the error term lies in an interval. Most of the time, when lambda plus 1 is not a perfect square, you get SO3, you get Batman. But lambda plus 1 is occasionally a perfect square. And what do you get? You get that one of Batman's ears vanishes, folds over to the other side, and it gives you the O3 representation. It has one vertical asymptote, and just more or less the right-hand side folds over to the other. And I find that very interesting. That's something that I didn't expect. And so this is very much like the kind of thing that you would expect for elliptic curves as a statement, but it's a little bit easier now for K3 surfaces. That maybe that's a little bit disingenuous, but this was an REU project, and you can do that in 6 weeks. So just in the last couple of minutes, I want to give you an indication of how you prove these distributions, because our methods are very different from the high-powered machinery that's required from symmetric power L functions. But I think it's really beautiful for other reasons, because it shows that the theory of modular forms give generating functions which are on the nose power moments, which I don't think anyone really recognized before. And I want to explain it, because what I just said was actually absolutely false. It's the theory of harmonic Maass forms. The Maass forms give on the nose these generating functions whose asymptotics I'm computing. So let me explain that. So to prove these theorem, of course, we use the method of moments. So what I want to do is pick a finite field, pick an M at random, and be able to compute the asymptotics of expressions like this as Q goes to infinity. So the last step is always the easy part, right? The part that people don't need to talk about. If you go back to your course on in probability, there's just a method. If you find some asymptotics, look up in a book. Look up in a book what the moments are distributions for. And if you break down a family of moments, in the book, it'll tell you what you got. O3, SO3, SU2, right? Why that works is, of course, a mystery. So loosely speaking, and I want to give an indication of how we arrive at this, because I think this is how we arrive at these theorems is perhaps more important than the statement of any of the theorems. Roughly speaking, our theorem said that all of these polar moments, from just basic facts about elliptic curves, are explicit. You can exactly write down these power moments in terms of the famous class numbers of Hurwitz and Gauss. There's a formula for it depending on a number of parameters. So I think you all know this. H of minus D would be the class number of a maximal order. Capital H of D and H star of D are those various class numbers where you begin to take into account orders that live inside the maximal order subject to some divisibility conditions. That's all. This is all standard. And as an example of the two F1 moments, if you have a finite field of order P to the R, where R is odd and M is even, the mth power moment is just this sum. It's just this interesting sum of class numbers. You're summing over finitely many S, which is, of course, designed to be in the Hasso range. And that's just what it is. What you need to be trained to see is where is the elliptic curve? Where does the description of this moduli space of elliptic curves appear in this formula? There are other formulas where the mth power moment, depending on congruence conditions and the shape of your field, tell you by law these power moments are finite sums of class numbers. In this case, you need to take into account the supersingular locus, which was excluded in the previous case. So we have a family of formulas like this. We have the same kind of family for 3F2, and it turns out that in these families that Roberts and Villegas are writing down, part of the built-in ingredients for their work is the possibility of constructing such formulas. That somehow comes for free from the Picard-Fuchs theory. So if you want to get these closed formulas, it's very easy. You don't need all you have to do is know how to do it. So this is a standard thing. If G is an abelian group and S is an integer that's of admissible size for counting elliptic curves, let IGSQ be a count of the number of isomorphism classes of elliptic curves over FQ, where the group of FQ points admits G as a subgroup. Like for the Legendre curves, it's Z2 is just there. And I want to count them so that the trace of Frobenius corresponds to that S. And rather famously, making Doiring and others explicit, a special case of this very famous but bizarre paper of Scopes, because it appeared in JCTA, Journal of Combinatorial Theory, Series A, but it was all about elliptic curves, states that in the case of the group Zn cross Zn, it's just this class number on the node. So I try to put different colors up there. So the red 4Q minus S squared is really about the Hasso range. Q gives you the order of the field. S is what the trace of Frobenius is going to be. The group is the N squared. So what you want to do is begin to see when you write down a moduli space of varieties, how do the arguments vary with your choice? So it turns out that if you want to prove these moments, you just plug everything in. I think you've all seen in Silverman, there's a beautiful 6-to-1 map that says that there are 6 isomorphic copies generically for a Legendre curve over FQ. Sometimes there's some collapsing, but we know how to work them out. And if you work it all out, you get our formula. So I hope that wasn't too fast, but it really isn't anything more than that. As the varieties get more complicated, that idea can still be worked out, but it becomes a little bit more delicate. So I will save you from that for the case of the 3F2s, but I will tell you that's what we did. We have an exact formula for all the moments for these varieties. The question is, so you have a formula, how do you do the analytic number theory to get the asymptotics? And here's the beautiful thing. It's been there. This is what the higher versions of the Eichler-Selberg trace formula are. If you study something called the Eichler-Selberg trace formula, you're taught to think that this is doing linear algebra on spaces of modular forms. But in disguise, Birch knew a long time ago that studying traces of Hecke operators was in disguise actually studying the family of elliptic curves ordered by J invariant, just all elliptic curves over a finite field. Let's now start imposing some structure on the variety, like some fixed subgroups, and then ask, when do they correspond to higher dimensional varieties? And that's what we have been doing. So if you've never seen this before, of course, you've seen Don Zaghier's name. One of Don Zaghier's major contributions, in particular, leading up to the work of Gross and Zaghier, is the discovery of one special function called H. It's been long known that the class numbers can occur as Fourier coefficients of half-integral weight modular forms. But for many years, it was believed that certain arithmetic progressions of discriminants were by law missing. Actually, this is something Andrew told me. You should study Gauss and prove some theorems about class numbers. And as a postdoc, I was always frustrated by this. I even wrote an Inventionis paper with Conan about class numbers, but I had to freely admit there were always some escaping arithmetic progressions because it isn't true that the canonical generating for class numbers is modular. Back then, I was afraid. I didn't want to try to work with harmonic Maass forms, which have as their generating functions all of the class numbers without exception. So Don proved that h of tau minus 1/12 plus this power series in red, which includes all the Hurwitz class numbers, is modular, but is non-holomorphic, and there's a small price you have to pay involving this Fourier expansion that's only mildly non-holomorphic. I'm brave enough after years to have a whole book on mock modular forms, so you'll see that I really like this function. And so I want to use this function to compute power moments. We should write this down somewhere. But if you revisit famous Euler identities, and Michael Mertens wrote a lot of this in his thesis, but let me teach you something. If you've seen these formulas that talk about how finite sums of class numbers can collapse to divisor functions, you may have first seen it in the context of factorizations of modular polynomials, which can be factored as Hilbert class polynomials, and then the degrees just add up to be things. And you may have been taught that that's how to think about these formulas. I want to erase that because that's really not, I think, the right way to think about it. So here's a toy problem due to Eichler that says if you fix an integer n and you just sum up the Kronecker class numbers in S aspect, you get a closed formula, some error term called lambda1, but it really wants to be a sum of the divisors of n. What I just told you about Don's function, it's almost like pretending that you had the right to compute h times the classical theta function and work with it as if it was just an ordinary modular form. But the truth is, if you learn some things about harmonic Maass forms and their differential operators, it's not you can almost think, you can actually do. And despite the fact these spaces of forms are infinite dimensional, we have the technology to reduce it to be to give exact formulas like this rather easily. Our more general problem is about moments, not just summing up class numbers. I need to sum up these class numbers weighted by even powers of S, which is, as you notice, the odd power. If you're wondering why odd power moments vanish in the theory of automorphic forms, this is one of the reasons. It's because of a degeneracy in the ring of differential operators. So we need asymptotics and M aspect for these sorts of sums. How do we deal with the S to the 2M factors? Well, I'm very happy to say, all I have to do is copy the previous slide and throw in some derivatives. If you differentiate a theta function m times, pretending that all the other parts of the Fourier expansion weren't there, all I'm doing is studying this infinite sequence. Well, maybe I'm not being fair to us. You actually have to do a little bit of work to carry this out, but the idea is that simple. All class number formulas, including the Eichler-Selberg trace formula, can be proven very, very easily, just as if you were checking a few coefficients in a modular forms identity if you just widen the ring. So I'm going way too long, so let me just, so we have the technology to do this. It involves what are called Rankin-Cohen bracket operators. It preserves modularity, but generally destroys holomorphicity, but never mind that, we know how to work with that. And so quite specifically, what I want to do in all of our formulas is to carry out this infinite sequence of bracket operators involving Zagier's H with just two theta functions. If you want to study other varieties, choose other theta functions and then do the geometry to write down the model of the object you found. And I think there will be a number of papers doing that sort of thing. When it comes to the asymptotics, let me just say, although these are non-holomorphic modular forms, we have a process of holomorphic projection that goes back to the 80s that allows us to do everything that you would ever want in the theory of modular forms. That part is easy. So you almost feel like I know how to find an Eisenstein series. I know how to find a custom form, and that's what you would be doing. What are some of the tools? There are things that you would expect. Deligne must appear someplace. That 1/4 is really Deligne in disguise in Hassan's theorem, combined with bounds, doing a little bit better than some earlier work of, I shouldn't name the names, but doing a little bit better than was known before for bounding Peterson norms for cusp forms. So to conclude, I hope this is interesting. If you're interested in sampling Picard-Fuchs varieties, There's generally some special function in disguise whose values encode the error terms. And in the three families that I showed you today, two of them give you back SU2 as you would expect for any family of elliptic curves with non-fixed J invariant. And I think this is the first explicit case of K3 where the rank is 19, generic Picard rank is 19, and you get Batman. And if you're wondering, as the rank goes down, what pictures do you get? It's awesome. Just stay tuned. All right, thank you. Yeah, so I gave the function f of 3 as that piecewise defined function.
Yeah, I mean, most of these functions have Fourier series, which is either 0 or 1 from some point onwards. The coefficients and cosines. I'm wondering whether Batman has a surprisingly simple Fourier series.
Well, yes. I mean, isn't that going to be like the hallmark of most compact Lie groups?
Well, that's what Katz-Sarnak guess, but
yeah,
is it true?
Yeah,
this may not be. I don't know.
Yeah, no, yeah, it's particularly simple, but I have to go back. Yeah. No, I found the moments. I literally did what I said. I looked up the. I can offer you as this as a clue. The asymptotic moments for Batman is a truncated hypergeometric function. So it's a twisted sum of Catalan numbers up to basically m if you're counting the nth power moments. And then you would have to infer from that. That's what I know. And by the way, that's going to be the hallmark. When you write down the power moments for SU2, you just get the Catalan numbers, but that's because there's a process that truncates a hypergeometric function that makes the rest irrelevant. And somehow, if this is related.
So for generic n, f, n-1, do you know the weights of the harmonic mass forms you expect to get out?
So that's not the right question. Right, if you do the Fn right, we don't know what the moduli space of varieties is going to be. You have to go the other way. So the right way to think is pick your favorite abelian group. What if I want to construct a Calabi-Yau manifold from groups over FQ that always have like a Z5 in them? You know how to do it over FQ, but then you need to build a global model so that global model actually inherits this. And then you find the hypergeometric function. Start with the group.
All right, let's thank Ken again for a wonderful talk.